Okay, beta elimination reactions. So beta elimination can occur via two mechanisms. So the same as substitution, nucleophilic substitution, we have SN1, SN2. We now have E2 and E1 reactions. So haloalkanes undergo elimination under basic conditions. So a strong base is required. So an example of that is sodium ethoxide. The process is called dehydrohalogenation, and we need a hydrogen atom on the beta carbon, which will be removed in the process. So the carbon that has the halogen attached, or the hydroxide if we're looking at dehydration, is the alpha carbon, and the next one is the beta carbon, and this beta carbon needs to have a hydrogen, and this one is removed, okay, to give you the double bond. Okay, so we've got the E2, which is the no carbocation intermediate, and the E1, which produces the carbocation intermediate. So irreversible reactions there. So let's have a look at the E2 elimination reaction. So the E2 is a transition state. Okay, so we've got the base coming in, removing the base coming in and attacking the beta carbon hydrogen and removes it, and while this is being removed we have the electrons going into the middle and then the X group coming off. So we have this whole transition state where the bonds are half formed, and then we have our product. So it happens in a single step through a transition state. Okay, so the transition state is when the double bond's starting to form and the hydrogen is starting to be removed. Okay, and this occurs under strong basic conditions. So E1 elimination reaction, so this is a two-step reaction. We have a carbocation intermediate, and this is under neutral or acidic conditions. So we have the removal of the chlorine. So the chlorine coming away, we've got a tertiary carbon here, so stabilizing that carbocation intermediate that is produced. We have the base come in and deprotonate the beta carbon, and then we have the double bond forming. Okay, so neutral or acidic conditions for the E1, and we have the carbocation intermediate. So what happens if there is more than one beta hydrogen? So you've got your beta carbon, and on this beta carbon you've got two hydrogens and a methyl group, and on this beta carbon you've got three hydrogens. So you can lose either beta carbon hydrogen, okay, so one off this one or one off this one. If you were to lose this one, you would get the double bond forming here, so between the two methyls. If you were to get it there, you'd be having so an ethyl and then the double bond between the two carbons. So the Zaitsev's rule says that you would get the double bond between the carbon with the most substituted carbon. So this carbon has no substituents coming off it besides hydrogen, whereas this one here has a methyl, so the more stable product would be between these two here. Okay, so that would be the major product. So substitution versus elimination. So there's a close relationship between nucleophilicity and basicity, and both of these processes will be occurring at the same time, and the one that predominates depends on several factors. So what are the conditions of the reaction? So looking here, just to remind you, substitution is when you have a group that's being swapped over. Okay, so swapping a bromine for a hydroxide in this case here. And elimination is when you're removing two groups and you're forming a double bond. So substitution versus elimination. So let's look at the relationship between elimination E1 and substitution nucleophilic SN1. So the nucleophile can act as a base and remove the proton. Okay, and then you can have the quenching of the carbocation, and this would give you your elimination product. Or you can have the nucleophile coming in and adding onto that carbon and giving you your substitution product. So once the carbocation is formed, you can have the nucleophile acting as a base or acting as a nucleophile and adding on. So with the elimination 2 and the SN2, the nucleophile again can act as a base, okay, giving your elimination product, or it can act as a nucleophile and come in from one side and then eliminate the leaving group at the same time. Okay, so remember your SN2 is that transition state, okay, and your E2 is the transition state, so the nucleophile's removing that proton as acting as a base, and we're getting the double bond forming all in the one step. Or if we're looking at SN2, we've got the nucleophile coming in from behind or from the front and the leaving group leaving from the opposite side. Okay, so for SN2, the nucleophile must approach from the opposite side. Therefore, if it's a large bulky nucleophile, then you're going to have the elimination proceeding. Okay, so the size of that nucleophile, if it's a large nucleophile, E2 is favoured. Okay, if that carbon bearing the halogen is easily accessible, so it's a small nucleophile and it's easily accessible for that carbon with the halogen or the leaving group on it, then the SN2 will be favoured. And that beta hydrogen is another limiting thing. So that beta hydrogen needs to be very easily available for your nucleophile to come in and act as a base. So this has all got to do with that steric bulk around your central carbons that are being attacked. So these two carbons here and the steric bulk around that nucleophile. So if the nucleophile is too big, it cannot come in and do this SN2 reaction. So therefore elimination would be favoured. And if there's too much steric bulk around here, then again this won't be favoured, so you'll get elimination. Okay, so let's have a look at the SN1, SN2, E2 and E1. Okay, so SN2 is favoured when you have an alcohol or alkyl halide. SN1 is your tertiary. So remember, we're looking at whether we can stabilize that carbocation that's being produced. When we have SN2, we have an inversion of that stereochemistry, so we've got it coming in from behind and pushing it out. And when we have our carbocation, we have a mixture of our R and S. So elimination, so E2 elimination occurs when you have a strong, bulky base, and E1 occurs not necessarily under basic conditions, it can occur under neutral or acidic conditions. So let's look at ether cleavage. So ethers are relatively unreactive, so the bond is fairly stable to bases, oxidizing agents and reducing agents. Okay, so ether cleavage is when you mix it with a strong acid and you will get the cleavage of this, and one side will get the X and one will get the alcohol. So ethers are significant for biological molecules, so the stability of them. So lipid molecules use ether linkages rather than the more usual ester linkages to link to fatty acids to the backbones of glycerols and sphingosines. This makes them more stable to hydrolysis and less likely to break. So as we've seen, the ethers formed by exploiting the reactivity of an alcohol and an alkoxide, and they can undergo cleavage under acidic conditions. So they're quite vigorous conditions, so concentrated acid and extreme temperatures. So now that we know the reactions and what functional groups we're looking at, let's have a look at some specific examples of different ones. So examples of alcohols, so substitution, so alkyl halide synthesis, we've got elimination, so dehydration, and we've got alkoxide formation. Next week we're going to talk about oxidation. Okay. So substitution of an alcohol, so alkyl halide synthesis is what's occurring when we're substituting an alcohol. So again, we've got our alcohol group, our tertiary alcohol, and we're going to be making our tertiary alkyl halide. So swapping that OH for a halogen. So for tertiary reactions, this occurs at room temperature. Okay, so we get the oxonium ion being produced, carbocation intermediate, and then the rate determining step, we have the bromine coming in and quenching that. Okay, so here are the different acids that you'd use for the different types of substitution. So if you want to add an iodine to an alcohol, you would use HI, get an iodine. If you want a chlorine, you would use HCl, bromine HBr, and fluorine HF. Okay, so if you want to do a primary alcohol and you want to add a halogen onto it, then you need a little bit harsher conditions, and they go via the SN2 mechanism. So butanol, you would use thionyl chloride, okay, and heat it a lot, and you'll get the alcohol attacking the sulfur. The sulfur would then, the thionyl chloride would then attach to it. The chlorine would be eliminated. Okay, so it's quite a complicated mechanism. You then have the chlorine coming in and kicking out that positively charged species, and that's where you get that SN2 mechanism. So we've got it coming in and coming out, and then we've got our chlorine. So this mechanism you do not need to remember. You just need to remember that for primary alcohols you need extreme conditions, and thionyl chloride would be used to get a chlorine attached, and phosphorus tribromide would be used if you needed to add a bromine to it. So the secondary alcohols can react via either SN1 or SN2 mechanisms under the different conditions, but they're just very slow. Okay, so they can proceed either way. It just depends on the alcohol and what you've got. Okay, so that's something you need to try in the lab to know. So elimination, so dehydration of the alcohol. So alcohols can be readily dehydrated to form the alkene, and this is done under acidic conditions. So again, we've got the formation of the oxonium ion. Okay, so we've got the protonation of our hydroxyl, formation of the oxonium ion. That makes a very good leaving group. We then have the oxonium ion leaving. We have the carbocation intermediate. We then get the deprotonation of the beta carbon, and we get the double bond forming. So remember, we need that beta hydrogen present, and this is done under acidic conditions. So water, great leaving group. Hydroxide is a poor leaving group, so by protonating that hydroxide we turn it into a good leaving group. So alkoxide formation, so we've talked about this before. So just another example of alkoxide formation, we've got meth, eth, propute, pentanol acting with potassium, and then we've got our pentan 1 olate as a product, and hydrogen gas. Okay, so concept check question. What is the most efficient way of converting a primary alcohol to an alkyl chloride? So if you've got a primary alcohol, you would then need to use strong conditions. So you would use thionyl chloride as your reagent. Why is it ineffective simply to react 1 butanol with HCl in the synthesis of 1 chlorobutane? So we've got 1 butanol and we want to make chlorobutane. So we want to change the alcohol to a chlorine, and we've got a primary. Okay, so there's not going to be enough of a favourable conditions for the reaction to occur. Okay, so we're going to need to use those harsher acids for that one. Okay, so if you did have the butanol with HCl, you would get the elimination product being formed, because remember, hydrochloric acid is in water. There's not much HCl, most of it's water, so you would get that acidic conditions and you would get elimination. Okay, so let's look at example reactions of alkyl halides. So we're going to talk about the Grignard reagent in topic 1.2, which is the next topic. So this time we've talked about SN2, SN1. So remember, so SN2 reactions is when you have the backside attack and you have the transition state intermediate. SN1 reactions is when you have the carbocation intermediate. And E2 reactions are with strong bases, and E1 reactions are under acidic conditions. So let's have a look at some examples. So the tertiary substitution reaction proceeds by the SN1 mechanism, and some of the reagents you can use are sodium hydroxide to introduce an OH moiety. You can use a sodium OR, so any kind of R group with an oxygen attached. And the sodium's the counter ion, and that will add on your OR group. So that could be a long aliphatic chain, or it can be a cyclic structure of some kind. Another one is your cyano group, so your C triple bonded to a nitrogen. So again, a sodium is the counter ion on that one, and that adds an extra carbon to the molecule. So this is great if you want to make your carbon chain longer. It's the only way that you can do it is with your CN group. Okay, if you want to add a nitrogen to the compound, you can add NH3, and this will give you NH3 plus Br minus. So we're making a salt here. So this is a salt that we've formed. You can also react it with water, and that will just give you a hydroxyl, so a OH group that's added onto it then. So it's the same reaction as the first reaction, it's just that the counter ion in this case is a hydrogen instead of a sodium. So the SN2 mechanism for primary, so again we can use sodium hydroxide. We can use sodium OR, so to introduce that OR group again. We can use sodium CN to introduce the carbon, so the cyano group. And again, we can use NH3 to make the salt, the ammonium salt. And again, we can use water. Okay, so here is a summary of those reactions in a pictorial kind of depiction. So we've got our haloalkane, and then we've got our nucleophile that's going to come in and substitute it, and then we've got our leaving group that's being produced. So the different nucleophiles are here. So these are an example of one. So you can have an OH, an OR, an iodine, you can have a CN, an NH3, or a H2O molecule. And these are possible counterions. Okay, so you can see if you just choose sodium, you're always going to be right, because sodium's a very good counterion for all of these ones. Because these are negatively charged, they're going to need something that's positively charged to interact with them in order for them to be available to act as a nucleophile in the reaction. Okay, let's have a look at a question here. So using 2-butanol, so meth, eth, prop, but, 2-ol. Okay, so 2-butanol as a starting material, design a synthesis of 2-methyl-butyl nitrile in 2 steps. Okay, so we're going to change the OH into a CN group. So how do we do that? So OH is a fairly good leaving group, but a better leaving group is one of your halides. So if we first swap it over with HBr, we can have our bromine group, which is a very, very good leaving group, and then we can use our sodium cyanide, and we can get the sodium cyanide there. Okay, so just noting here that because this is a secondary alcohol, we could use HBr or PBr3. So remember, PBr3 is what we use for our primary ones, and HBr is what we use for our tertiary substitutions with our halides. So secondary, either way would work, but you'll just have to wait a little bit longer. So draw the structural formula for the major product formed when 1-chloro-1-methyl cyclohexane is reacted under the following conditions. So we've got CH3CH2O Na+. Okay. So if you can remember, that is the structure of a strong base. So the strong base that is the structure for is sodium ethoxide. So we've got sodium, meth, eth, and we've got an oxide. Okay, and this is under ethanol conditions. So this strong base would be removing the beta hydrogen. There's 3 different beta hydrogens that it could possibly remove. And we'll be making an alkene. So remember Zaitsev's rule, the product with the most substituted carbon will be the one that makes the double bond. So in this case it would be between this alpha beta or this alpha beta, you'd get the same product. Okay. So these two are the same thing. If you name it, you'll get the same name out of it, and this one would be your minor product. Okay, so is the reaction between 2-chloro-2-methyl-propane with sodium hydroxide, SN1, SN2, E1 or E2? So first of all, what sort of conditions? We have sodium hydroxide. This is a base, but it's not a large bulky base, so it's going to act as a nucleophile. And we've got 2-chloro-2-methyl-propane, so that 2-chloro would be substituted. We've got a tertiary center, so it will proceed via the carbocation intermediate, and the carbocation intermediate is our SN1 reaction. Okay. Okay, so let's have a look at some questions. So we want to predict the major products formed from the following reactions and what mechanisms predominate. So our first one is this structure here, and we've got sodium cyanide as this reagent here. So we've got a small nucleophile, which is the CN, and the sodium is the counterion for that one there. So we're going to have a substitution reaction occurring, and it's going to be a SN2. Okay, so we've got an SN2 here. So we've got inversion of our stereochemistry. Okay. So the reason it's SN2 is because it's quite easy to get into this carbon here for that small cyanonucleophile. So B, okay, so we've got a similar kind of structure here. We've got a tertiary carbon, we've got a good leaving group, and we've got ethanol, which is not basic or acidic. It's a neutral kind of solvent. So we're going to have the O ethyl group displacing the chloro, okay, and that again with the tertiary carbocation there would be SN1. So remember, protic solvents such as ethanol would make this reaction very slow because it decreases the nucleophilicity of the nucleophile, so it decreases that nucleophile's ability to act as a nucleophile because it will be interacting with all the other protons around in solution and blocking it. Okay, our last one here. Okay, so we got a strong base here. Alrighty, so we've got terbutoxide. Okay, so it's a strong bulky base. It won't be able to fit in there to displace anything, so it's going to be an elimination product. So it's going to be removing one of these beta hydrogens in the process, and it removes the one that's the most substituted, so the major product would be removing this one and forming the double bond between these two, and the minor product would be between one of the other ones. So it'll look like that one, so your major and your minor. Okay, so that's an E2 mechanism there because it's a base. So remember, E1 is under acidic conditions. So let's have a look at acidic cleavage with HBr or HI, an example. Okay, so let's have a look at this. So we've got our strong acid which protonates our ether, oxygen. We then have the iodine species come in and remove the proton, and then this makes we then have the iodine species come in and remove the methyl group, and this makes the lone pair of electrons here quench that positive charge on the OH, and we get the hydroxide, so the alcohol being formed, and we have the methyl iodine as a product. Okay, so we've got a carbocation intermediate, so we're going for an SN2 reaction here. Okay, so we've got the same one similar to what we had before, actually exactly the same one as we had before, and we've got the HI coming in, and we've got our hydroxyl alcohol group, and we've got our methyl iodine. Okay, and we could also have a different kind of non-cyclic structure, and we would get the same product. So we'd have the cleaving down here, and we'd have the OH, and then the iodine would add to the other side. So let's have a look at some other examples. So just more examples for you to see. So ammonia, a neutral molecule, can be substituted with a haloalkane producing an alkyl ammonium salt. So we've got a haloalkane. We've got the alkyl amine, so our amine group in the middle, so NH2 is our amine. We then have this reacting SN2 reaction. Then we've got our salt formation, so our nitrogen adding on to the group there, and it's formed a salt. Okay, so then if you treat that with base, you could then remove that extra proton and go back to having just the amine there. So we've got here, we have a haloalkane, we have sodium cyanide, so our cyano group, and then we would be displacing the bromine, adding our cyano group on. Okay, so making a new carbon-carbon bond, and then from that one there we've got a triple bond. We can reduce that triple bond down to the amine, which we'll learn about next time, or we could hydrolyze that triple bond to form the carboxylic acid. Okay, so these are two reactions we'll talk about a bit later in the semester. Okay, so you probably all are aware that cyanide is very toxic. Okay, if you can smell it, you're probably dead already. So we tend not to use it, but it is a great way of adding carbons to molecules. So here's a higher kind of question. So how would you prepare this ether from cyclohexanol? So cyclohexanol, okay, and we want to make this ether here, okay. So we need to make sure we have a good leaving group. So usually we use a halogen, and the first thing, so an example is HCl. It's secondary, so it can go with HCl or it can go with thionyl chloride. So HCl or thionyl chloride because it's secondary. Okay, so introducing that chlorine group, and then you would add in your base, so this one here. Okay, so that could have the hydrogen or it could have a sodium counterion, and then we would get our ether. Okay, so this is our learning objectives, and I'll let you have a read through this in your own time. So thank you for listening to my recording, and I hope that you've had enough information here for you to go onto your cheat sheet. There are lots of really good websites online that can help you, give you a little bit more information on a specific section if you're having trouble with, or you're always welcome to come up to my office and sit down and have a bit of one-on-one chat and see if we can explain it in a few different ways, so that way you can fully understand the concept so you can move forward. Remember, these recordings are not a replacement for the lecture. We talk about more things in the lecture, but this is kind of a summary of what we talk about in the lecture.